everybody. Today we're going to do something a little tiny bit different. We are going to talk about the scientific method. So now that we know some of the areas that scientists study, we're going to take a look at what scientists do. Scientists ask questions about the natural world, but there are a few questions science can't answer. Questions about art, politics, personal preferences, and mortality, or what happens after your body wears out and you die, are just a few of those types of questions. Scientists do look around. They ask questions about the world around them. Often they're looking for ways to improve the world they live in. They conduct research to get background information about the problem and find out what's already known. Next, they make an educated guess or form a hypothesis or a prediction of the answer to the question they've asked. Next, they do research and experiments to test their hypothesis, to make observations and collect data during their experiment. Once they've interpreted the data from their experiments, they come up with a result or a conclusion to determine if their hypothesis was correct or not. They then communicate, present, or share the results of their experiment. Now, good scientists repeat the process to show consistency in their hypothesis. And telling others about your findings and how they can improve their surroundings is especially important. This is called the scientific method. Once a scientist has completed their repeated experiments, there are a few different outcomes to find that outcome was correct. All the questioning, research, experimentation, and presentation of their results have resulted in support of their theory. Another option is that they need to change parts of their hypothesis if their experiments aren't quite proving what they want. Should they change their hypothesis? Should they change variables in the experiment? Those are all great questions that would require the scientists to start again. A third option is that the explanation of the original hypothesis changes. Another result that can be drawn from their conclusions is that they need to just throw it out. Whether their hypothesis is so far from what the experiment is proving, or their question can't be proven scientifically, the result would need to be thrown out. Now, all four options are important. Scientists need to be able to persevere through the frustrations of all those outcomes. And all four outcomes are extremely important. Learning from what we feel like failures are just as important, maybe even more important, if you ask me, than getting it right the first time. One of my favorite examples of this is Thomas Edison. Now, Thomas Edison's teacher said he was too stupid to learn anything. He was also fired from his first two jobs for being non-productive. As an inventor, Edison had 1,093 patents. Among his most famous patents was the incandescent light bulb. While working on the light bulb, he made 1,000 unsuccessful attempts. When a reporter asked, "How did it feel to fail 1,000 times?" he replied, "I didn't fail 1,000 times. The light bulb was an invention with 1,000 steps." That's the job of a scientist, to persevere in answering the question of how to make the world a better place. If you're interested in learning more about Thomas Edison, click on his picture and see what history.com has to say about his life and accomplishment. All right, let's chat for a few minutes about the difference between scientific theory and scientific laws. A scientific theory is an explanation for why things work or how things happen. Scientists develop theories based on their observations of the world around them and have to be able to be tested. Some examples of life science related theories are cell theory, the theory of evolution, the theory of relativity, and the germ theory of disease. A scientific law, on the other hand, has been proven through the scientific method. No matter the circumstance, a scientific law always happens. A scientific law doesn't try to explain why, but instead shows through repeated observations and experiments that that law never changes. A few examples of scientific law are the law of gravity, the laws of motion, the law of conservation of mass, and the law of conservation of energy. The conclusions made during experiments can be made in two ways. The first is by making inferences about the experiment. Inferences are based on your prior knowledge and how it relates to you. The New York Times has a series called "What's Going On in This Picture?" They post pictures that have no captions and ask students just like you to make inferences about what could be happening in the picture. This is an example from May 11th of this year. Based on what you know, what do you think is happening in this picture? Use the upcoming discussion thread to discuss with your classmates what you think is happening in the picture. Now, the other way to make conclusions during experiments is by making observations. Observations are based on things you can see or measure in the experiment. There are multiple ways to measure volume, length, area, and width. You can make quantitative and qualitative observations. Quantitative observations are all about the numbers. They're measurements made with instruments like those on the last slide. You can measure weight, height, length, distance, and volume. Qualitative data, however, is based on things you can see, smell, hear, touch, and taste. Things like color, experiences, and emotions. Now, looking at this picture, let's write some examples of quantitative data from this picture. Remember that quantitative data is represented by numbers. For example, let's say this cat weighs 6 pounds, 3 ounces. That's one piece of quantitative information. The chair seat is 3 feet 6 inches from the ground. The plant's pot is only 3 inches from the edge of the table. The cat's tail is 14 inches long. Notice that all these data points have specific measurable data. If you or I were to measure all these aspects in the picture, we would both get the same measurements. Looking at the qualitative data, there are things like the cat is black and white. The cat has green eyes. The cat is lying on top of the table, and the plant is near the edge of the table. As long as I haven't used numbers to describe the picture, the data is qualitative, or shows what I look at. What's in the box? Have your learning coach put an item into a box and close the lid so you can't see what the item is. Don't cheat. Try and look. Next, use qualitative and quantitative data to figure out which items your learning coach has put in the box. Keep track of your data to answer the questions on the next slide. Once you've used your data to determine what's in the box, have your learning coach put another object in the box and repeat the process.